Hi everyone, for my week 14 project, I will present the Theorem 4.6.3, also called the plus-minus theorem. I will explain the idea of the proof in my own works and then show you two examples that I use in the theorem. So let's start from the part A. So if S is a linearly independent set and if V is a vector in V that is outside of a span S, then the set S with V that results by inserting V into S is still linear independent. So how to prove that? So for the A, we assume that the S equals to S1, S2 to the Sk is a linear independent and that V be a vector that's not in span S. So we want to show that S equals to S with the V, right? So it's also a linear independent. Assume a linear combination in S equals to 0 vector, which is C1S1 plus C2S2 plus to the CKSK plus CV equals to 0. And the rearranging gives that CV equals to negative C1S1 plus to the CKSK. And if C doesn't equal to 0, then we have V equals to negative 1 over C times C1S1 plus to the CKSK, and which expresses V as a linear combination of vectors in S. This contradicts that the consumption that V exists in S span S. Therefore, C equals to 0. Then we have C1S1 plus to the CKSK, which is 0. And since S is linear independent, the only result is C1 equals to C2 equals to blah 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 to the CK, which is both 0. False, all coefficients are 0, proving that S in a V is a linear independent. So we prove the 1. And then we move on to the B. So to prove the part B, if V is a vector in S that is expressible as a linear combination of other vectors in S, and if S2 minus V denotes the set obtained by removing V from S, then S and S minus 2V span the same space, that is span S equal to span S minus 2V. So we should assume that S equals to V S1 S2 to the Sk, and suppose V equals to A1 S1 plus 2 AKSK. So we should let S minus V, and we want to show that span S equals to span T. So how to show one like span T to then span S? For one, this is opposite because one reason is T is to the S and show that every vector of S expects V is already in T. So we only need to check that whether whether V in a span T. But that is true because uh, we have v equals to a1s1 plus 2 aksk. So where all the si exists t. Therefore, all vector in S are in the span T. So we got the span S equals to span T. That's easy, right? And now we move on to the example. So example 1 for the part A, we have so let S equals to 1 0 0 0 1 0. This is a set that is linear independent, so we should let v equal to 1 1 1. So check whether the v exists in span S. So we have a times 1 0 0 plus b times 0 1 0 equals to 1 1 1. And has no solution because the third coordinate must be 0. Therefore, the v doesn't exist as in a span of S. And by the plus part of the theorem, we can have that S with the v is still a linear independent. And then we move on to example 2. So let S equals to 1 0 0 1 1 1. So we should notice that 1 1 1 1 equals to 1 0 plus 0 1. So it is a linear combination of other vectors. If we remove it, we have a t equals to 1 0 0 1. Then the span S equals to span T equals to R square, which is in 2D. And then thus removing a redundant vector does not affect the span. So we prove it. That's all. Thank you.